cyanide. And that's a much weaker CO, which is because it's a bridging CO. And you have done this in iron, diiron, nonacarbonyls, dodecacarbonyls. The bridging COs have a distinct lower vibration than terminal COs. That's exactly what's going on here. So without knowing the structure, you can pretty much say with a lot of confidence this is the molecule I made. And you have a cyanide, you have an open site. Great. Is this any good? Turns out it's pretty okay. Now this is where we do solution structure using exact analysis with someone in UCL, Steve Kramer. And this gives you scattering, don't worry about the technique. So this gives you the bond length and it's consistent with what we're saying. Now, now what happens? We make hydrogen by chlorinating the cluster and reducing it. Previously we had to go to 1 normal acid. Now we can work at 0.005 normal acid. We need much lower acid. Okay? Once we put in the cyanide. Now also in electrochemistry, whenever you see a current like so goes up and then saturates, these are called electron transfer, kinetic region, mass transfer region. I don't think that's what I'm supposed to teach because it's a little technical. But then again, here's the poor man hydrogen detection using platinum ring. It's all good. Now, the reason why I said this electron transfer, where electrode to catalyst electron transfer is rate limiting, and this is where proton diffusion is rate limiting. Don't get into the details, but you can expect the rates of reaction, and the rate of proton reduction by this guy is 2.5 into about 11 mole inverse second inverse. Now, what is the fastest reaction in water?
Acid-base reaction.
What's the rate of that by molecule? Any idea? So 10 to the 12. So this is a very fast system. Now, so when we were dealing with this complex without the cyanides versus when we dealt with the cyanide, what happened? Putting the cyanide increased the electron density of the cluster. And that manifested itself in two ways. One, the CO vibrations spectroscopically went down, consistent with back bonding. Two, protonation became easier of the cluster, making it a better hydrogen catalyst. Now, I'll give you a little mechanism of how these things work. The cluster in its native state is iron 1, iron 1. So it needs to be reduced to iron 0 before it can make hydrogen. Okay? And then once you do that, the proton goes and binds over here, becomes a hydride, picks up a proton from here, and makes hydrogen, which is why this base was very important. So your open site brings in a proton over here, which gets reduced to make a hydride, and this ammonium ion gives you the proton to make dihydrogen. Okay? And this is why such a catalyst with the open site, pendant nitrogen, cyanide to assist protonation was much better than the previous one, where there was no open site. For all practical purposes, the hydrogen would have been going somewhere in the middle because there was no asymmetry in the catalyst in the middle. Now, let me demonstrate to you how important this nitrogen lone pair actually is. So, in the system that I've been talking so far, you see this phenyl ring with this azide ring. So, what you have is SCH2N, just behind that another CH2 and S. And these are aromatic rings, aromatic amines. So, of course, the nitrogen lone pair is in conjugation with the ring, which means they do not have a very high pK, which is why I have to go to 10 to the power -3 type acid concentration to get this protonated reaction work. But now what we did is we realized the problem and we substituted the 2 position of the phenyl ring ortho with simple alkyl groups. And when that happens, what you see is the aromatic ring flips because it's no longer able to accommodate the resonance because of state difference. And as a result, if you see the nitrogen over here, it's almost sp2 then. Here it's sp3. So now, what one would call a simple modification, but this is where your previous knowledge leads to new directions. Our previous knowledge led us to believe that we needed we had a problem over here, and we used that, and you can see now this is sp3. And more importantly, the nitrogen, sp3, if you can imagine a lone pair inside over here, pointing towards the cluster. And you need that, because that's going to accept the proton, give it to the cluster. So you need that orientation. And this is some representation of the same thing, using planes. Now what happens, this guy starts making hydrogen, like so, Bowman's technique, but now we have a GC. But we still do that because that's in situ detection, which is better. Now, this can do this at neutral pH 5.6. So what we had to, initially we were at pH 1 without the cyanide. Then with the cyanide and open site, we came up to pH 2.5. Now we realized the problem with the nitrile lone pair, flipped the ring, met the lone pair sp3. Now we are making hydrogen at neutral pH. So now this lone pair is quite basic. Picking up proton at neutral pH, giving it to the cluster. You have neutral pH hydrogen. What's really very anticipatory, and this is what happens. You try something brave, because this synthesis took us 2 years, because it wasn't easy putting something in the two-place every setting. But you get rewarded in ways you didn't imagine. See, but then also you have to be observant about things. So when you do a cyclic voltammetry, these guys are notorious, they don't give you good CD. But what happens, the cluster in its 1,1 form gets reduced to 1,0 form, then gets reduced to 0,0 form. This 0,0 form, in aqueous solution that is in heterogeneous electrode, you pick up the CD, but you can also pick up the CD of this 1,0 to 0,0. But it's difficult to see because it starts to make hydrogen. Okay, because this is once it becomes ion 0,0, it makes hydrogen and the hydrogen current picks up. But what we noticed is, depending on how much hydrogen current we were generating, something here was going in. So initially, if we went up to this low, there was nothing. Little bit of hydrogen generation current up over here, more hydrogen generation current up over there. So we thought, what is this thing happening? In electrochemistry, anytime you see a peak going up like that, that's deposition. That means your catalyst is degrading and then it's deposing. I mean, seriously. I didn't even talk about oxygen. Okay. So what happens is, this complex is capable of making hydrogen as well as oxidizing it back. So this is, in a sense, a true mimic of the enzyme, which can go both ways. It can make proton to hydrogen and hydrogen to proton. And as a result, this lone pair became so effective because as it is, you reduce it by 2 electrons, picks up proton and makes hydrogen in the process. Or this can take hydrogen in its oxidized form and split it into proton and hydrogen. And it can do so because it has a very strong base to accept the proton. And the hydride goes on the iron. And that's why you have what you call a bidirectional catalysis. Something that aligns with the principle of microscopic reversibility. That every reaction happens the same way, even if you come back. And this catalyst can do that. Now, your 5 minutes, did you really?
You got to watch.
But did we start?
2 o'clock.
Since?
Yes.
We were there at 2 o'clock. Okay. So now, because of the strict guidelines, I'll try to tell you how we dealt with the final obstacle, that how to deal with the fact that it's not stable in molecular oxygen. And for that, we actually did an investigation with our complexes at hand to find out what exactly was going wrong in the presence of molecular oxygen. And what we realized, oxygen was getting reduced to H2O2. And this H2O2 is detrimental to any living species or catalyst, and was oxidizing the thiolates on the cluster to sulfoxides. And that's why it was degrading. So we could prove it in different techniques, so we realized that was the problem. So we are faced with a competition, a low valent metal reacting with proton versus the same metal reacting with molecular oxygen. How do you control this? So there are 3 ways you can do that. You can either deal with the H2O2 that's coming up, decompose it with some means that should help, or you can reduce oxide to water instead of H2O2. Water won't hurt, or if you could reduce proton selectivity in the presence of oxygen. And it's like, ultimately you'll see the solution is just like Indiana Jones, where the cheapest looking grain is the right one. So we tried using enzymes to deal with the H2O2, but it's an expensive solution. It works, it's an expensive solution. We use iron porphyrin complex to reduce oxygen to water. It works, but then the most sophisticated one, we saw if we could somehow take a metal complex and reduce it, but the proton needed will go to the ligand and not to the metal. So the metal will not participate in proton reduction, but the ligand. So if the metal is not participating or it doesn't have an open coordination site, then neither proton or oxygen can go. But if the ligand can be reduced and the ligand accepts the proton, the chances of ligand directly reacting with oxygen will be low. So ammonium tetrathiamolytrate, there you go. My tetrathiamolytrate for you in your polyoxometalate domain. You take ammonium tetrathiamolytrate, and what you see is you take a gold electrode and you do an electrolysis, that is, will generate hydrogen. You will see, irrespective of whether you have oxygen or not, you see the same current. Which means, even in the presence of oxygen, it generates hydrogen in the same rate, in the same time, essentially, that it does in presence of oxygen. And that's because ammonium tetrathiamolytrate forms this nice insulating layer of gold, which is about 4 nanometer long, which you can characterize with a bunch of different methods. And this monolayer avoids any direct interaction of the oxygen with the electrode. It hits the ammonium tetrathiamolytrate, and the mechanism is as such: the ammonium tetrathiamolytrate, the molybdenum center remains tetrahedral because of the assembly, so the proton can never go and bind molybdenum. It actually binds the thiolate sulfur or sulfide sulfur. As a result, it does not matter if you have oxygen, if you have carbon monoxide, if you have brine, sodium chloride, because the metal is not involved, none of this inhibits this catalyst. And that sort of was our first breakthrough. These are very energy efficient catalysts with zero potential, and it compares fairly well with platinum. And what's really interesting is we went around and collected water samples from all over the world, and depending on where you get the water from, including Dead Sea in Israel, it doesn't matter. You know it's going to work simply because the metal is not involved in any way. It's the sulfide which gets protonated, and when you put electron, the sulfide gets protonated, taking protons from water, and that generates hydrogen. And there is nothing on the metal. So as a result, irrespective, we put like saturated CO solution, sulfide, that would kill anything. Dead sea water, that kills everything. It works just fine. This is a slow catalyst, but it's a great catalyst. And now finally, can you think of a metallic system where the metal binds proton and generates hydrogen, but the metal does not bind oxygen? Is that possible? I have a reduced metal. It will bind proton, so it is an open coordination site, but it will not get reduced or not bind oxygen. Well, apparently it is. And here's a last video I'll show you. Now I have the second part of the lecture which I cannot go into because I guess there's a limit to the amount of gear one can do. Now here's a video. 5 ml hydrogen in a minute, because that's how much you need to generate to sustain combustion. And this is a graphite electrode with a catalyst on top which binds protons, makes hydrogen out of it, but does not bind molecular oxygen. And we're collecting the hydrogen that comes out through a delivery pipe over here. Sorry, the chemistry is mature, but the videography is amateur. So right over here, you can see the meniscus going down because how fast the hydrogen is getting generated from that small electrode. And that's like 100 ml per, you can very easily generate 100 ml of it in this small setup in like a couple of minutes. So this is like in 5 minutes, imagine this full and the entire electrode generating hydrogen, that's a lot of hydrogen. And you can see steadily the collection happening. And before you know, within a minute or 55 seconds, you get 5 ml that will go to the target. Yes, we did target, otherwise I will tell you this. How do you make your hydrogen and oxygen? You light it. And you won't hear the noise, but you will see the explosion that scared both me and my student who was doing this. So essentially, that's the whole idea. If you can generate hydrogen this fast, so from a solar PV panel, you should be able to generate hydrogen in situ for your car, because cars generally do not consume a lot of petrol when it works, it actually consumes a very little bit. Otherwise, our petrol will be exhausted within 1 mile, right? There's a limit. But anyway, I leave you with this because he looks very angry. Just with one thing, I could not talk about water oxidation because of the relaxed and slow pace I decided to go. But I want to give this message: any water oxidation catalyst has to be a metal oxide or a polyoxometic. It just has to be. Because water oxidation involves very highly oxidizing intermediates. So anytime you have a carbon, nitrogen, hydrocarbon, it doesn't matter, an organic legal framework, it will be degraded in a very short time. Remember, when you make a catalyst, that has to last months, years. It cannot just last 10 seconds, 20 seconds, 1 hour, that's not good. Which is why our electrolysis are at least 1 day long. And we don't see decay. So, and also what happens is anytime you have metal oxide type catalyst, any metal that comes off, because you are oxidizing, you have a positive potential, again forms metal oxide and goes back. This is very obvious, but people have given it a very fancy name, self-healing. It's a very obvious property actually, for an organic chemist. So essentially all you have to do is control the overpotential by good choice of anions and increase conductance of the metal oxide layer. And he's standing up. You really don't want me to tell you about any of this, right? You sure? You sure? Look, a dinosaurus picture is there. No? Even that's not good? Seriously, we did no setup by 1,000 times. Not good? Okay. No, I'm sorry, I just did a very relaxed pace, and of course, he didn't tell me that this is what undergraduate students. I don't know if there is any, but I slowed down from there. But if you do have any questions, I'd love to answer them.
Thank you. Okay, so if you have questions, please. In your second catalyst, the one with this, I'd like to thank Abhishek, and we have a short break. So, and then we will reconvene for the discussion with Craig in 15 minutes time.